Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself Professor Anjali Pal. We are both from Civil Engineering Department, IIT Kharagpur. This is module 2 and this is the chemical equilibrium. We have divided this course into two parts. The first part is environmental chemistry, which will be covered by me, and the second part is the environmental microbiology, which will be taught by Professor Sudha Goel. Now, I am coming to my 9th lecture, and this is on the chemical equilibrium. The topics covered in this lecture will be dissociation of acids and bases, dissociation of water, equilibrium concept in complex formation and dissociation. Ionization of acids and bases we have already seen in the acid base chapter. We all know that according to Arrhenius theory, an acid is a compound which gives H plus ion in water, and a base gives OH minus ion in water. So, Arrhenius theory helps us to explain the strength of acids and bases. Strong acids we know that they fully dissociated, 100% dissociated in dilute solution, and for example, we have seen that HA, which is a monoprotic acid or monoprotonic acid, which gives H plus ion and A minus ion, and in case of acid dissociation we always write Ka, that is in this case it is H plus ion concentration into A minus ion concentration by the concentration of Ha. Now, what we will infer if the Ka value is very high or Ka value is low? For a strong acids, the Ka value is very large, as because this Ha concentration is almost undissociated, no undissociated acid in case of strong acids, that is why Ka value is very large. And in case of weak acids, say for example, acetic acid, we all know that acetic acid is a very weak acid. In that case, we write HAC is nothing but it decomposes into H plus ion plus acetate ion, and then in that case we can write Ka is H plus ion concentration into Ac minus ion concentration by HAC, and we can see from the value that it is low, very low. At 25 degrees centigrade, it is of the order of 10 to the power minus 5. So, it is a weak acid, it dissociates only a very small fraction, means degree of dissociation is low, not like the strong acid. Now, in case of diprotic acids, it is a very important example. This is the carbonic acid, it is a diprotic acid. You see here H2CO3, that means 2 protons are there. So, what will happen when first dissociation occurs, then H2CO3 will give H plus ion plus bicarbonate ion, and here we can write that Ka1. For the second dissociation we can write Ka2. Now, in case of Ka2 for this carbonic acid, we can see the value here, it is a very weak acid, it is very weak acid. If we know the pKa value, it is the minus log of K, then we will see it is just below 7. Okay. And from this pKa value we can easily tell that it is a very weak acid. Now, in the second, when the second deprotonation occurs from the bicarbonate ion, this bicarbonate ion will give H plus ion plus carbonate ion, and then in that case Ka2 can be written in by this expression, and the value of Ka2 is 4.69 into 10 to the minus 11. It is very low, and in that case we can write that it is when we determine the pKa, then it is seen that it is in the alkaline range. Now, For ammonia, which is a typical weak base, similarly we can write ammonia plus water gives ammonium ion plus OH minus ion, and in this case we can write Kb, which is nothing but ammonium ion concentration into OH minus ion concentration by ammonia concentration, which is also the 1.75 into 10 to the minus 5, and pKb is minus log of Kb. So, we can easily get from this value. Now, regarding the ionization of water, this has been explained in the acid base chapter, and then here again it is written, just to recapitulate, that in aqueous solution the most important equilibria is the dissociation of water into H plus ion and OH minus ion. A proton, we all know now that the proton cannot exist because it has a very small volume. So, the extremely large charge to volume ratio it is having. So, it is immediately it reacts with another water molecule, another molecule of water to form the hydronium ion or hydroxonium ion. So, basically it is better to write this equation, but for simplicity purpose we always use this this dissociation expression, this water dissociation expression. Now, it gives us the ion product of water. We know that from the equilibrium expression we get the equilibrium constant, that is the equilibrium constant is expressed in case of water as Kw. It is nothing but the ion product of water, and the water concentration here from the rules we know that it is taken as 1. Now, Kw value also we know at 25 degree is very low value, 10 to the minus 14. It is important to remember, that the numerical values of H plus and OH minus will include, what it will include in a system when you consider the H plus ion concentration and when you use the OH minus ion concentration. What do they include? They include all the H plus ion concentration and all the OH minus ion concentration, whether they come from water alone or they come from other constituents that is present in water. This is very important. I have shown you that day the seesaw, that if H plus ion goes up, then OH minus should go down. So, but it is here it is written that what is the H plus ion concentration, from water it is coming, from other species it is coming. So, everything together, that is the H plus ion concentration. Same is true for OH minus ion concentration. We should not forget this one. Okay. Now, complex ion formation and dissociation. It is also very important to know the complex ion. If some complex ion is formed, how we should write and what we should consider. Okay. In complex ions, we observe the presence of, what is a complex ion? If you consider a complex ion, say for example, this one AgNH3 twice plus. Okay. In this ion, what we see? We see that there is a metal, metal ion, and this metal ion is complexed with something, is associated with one or more ions. It may be ion or it may be molecule. So, here in this case it is molecule, but some cases it may be ion also. Okay. So, metal associated with some ligand, they are called ligand, and common ligands we know that they may be OH minus, this ion, carbonate, this also ion, ammonia, fluoride, chloride, cyanide, thiosulfate, all these can act as a ligand. Okay. And some species like EDTA, ethylene diamine tetraacetic acid. Humic acid is a natural ligand. Okay. In the humus substances, we always see it is a natural color forming agent. It has a very complex structure, and they also can combine with metal ion to form the complex. Okay. For example, silver plus ion forms a complex with ammonia to give silver ammonia or silver amine complex, is having this structure, and it is in equilibrium. Now, so here the formation, here how we will express? In case of acid we say it is dissociation constant. Okay. In case of ammonia also dissociation constant, that is base, weak base. Okay. And then in case of say water, we write the ion product of water Kw. In case of this complex, how will you say? In case of complex we write that it is the formation constant or stability constant. Okay. And usually beta term, by using beta term we express. Like previously we have seen that solubility product, this is also an equilibrium constant. Okay. For solid substances which is insoluble, insoluble compounds, we usually this term is very important, that is the solubility product. So, here all such complex ions are destroyed by removing one of the dissociation products. Taking this example, say for example, silver amine complex is produced from silver ion and ammonia. Okay. Then this complex may be broken down. Now, you have the some idea about the shifting the equilibrium, right. So, if I want to shift, okay, this has been dissolved, silver plus and ammonia forms the complex, it is a dissolved state. Okay. Now, if I want to make this reaction in the go to backward reaction, then how will you do it? How will you do it? Then if we want to do it, some product here, in that case these are the products, but some product has to be removed. How you can remove it? You remove it. So, for example, if you want to remove the ammonia that is produced, then how will you remove it? You put it some acid. Okay. Then in presence of acid, this ammonia will form the ammonium ion, which is very stable, and then ammonium ion will go into solution, then slowly the reaction will go to the backward direction. Okay. All such complex ions are destroyed by removing one of the dissociation products. This is the dissociation product. When this is dissociated, it forms this one. So, one of the dissociation products, if you can remove it, then it will go towards the backward direction. For example, silver ammonia complex ion can be destroyed if some source of H plus ion is added, because upon addition of H plus ion, NH4 plus is produced, which is more stable. So, ammonia will be removed and ammonia will be removed as ammonium ion. So, more and more silver amine complex will be going towards the backward direction to produce more ammonium ion, ammonia, and then again acid is there. So, it will be removed. So, slowly it will be totally broken down to silver plus and NH3. So, this is the concept actually. Now, formation of complex ion, here it is shown a very really complex. What is the complex ion? Here it is shown. It is shown here as a typical example. Let us consider the formation of complexes between mercury 2 plus and chloride. Why I am saying it complex? Because in different proportions chloride can add up to mercury 2 plus to form different species. Okay. At different proportions it can add. Okay. How? It can form say Ag2 plus, it can combine, chloride can combine with Ag2 plus to form AgCl plus, it can form AgCl2, it can form AgCl3 minus, it can form AgCl4 2 minus also, depending on how much chloride is combined. Okay. So, here there are many all the expressions, equilibrium expressions are shown, equilibrium reactions are shown. So, Ag2 plus, when only one chloride ion is combined, then AgCl plus, then another chloride is combined with this one, then AgCl2, another chloride is combined, then this is forming this one, then another is combined. So, all 4 chloride ions are combined. So, it is formed AgCl4 2 minus. Okay. Now, separately we can write the equilibrium expressions, like for the first reaction we can write K1 is nothing but AgCl plus concentration by Ag2 plus concentration into a Cl minus concentration. Similarly, for all reactions we can write K1, K2, K3, K4, and these all are obtained, these value K values can be obtained from the literature. Okay. Now, it is also possible to consider the overall reaction by combining the stepwise reaction. So, in the previous case we have shown single steps, okay, but we can combine, say for example, these two if I combine, okay, then what will happen? Ag2 plus 2 Cl minus, then it will forming AgCl2. Okay. If I combine these 3, then HgCl2 plus 3 chloride minus will give this one. So, by combining also we can write in this fashion, okay? HgCl2 2 plus Hg2 plus Cl minus giving this one, then Hg2 plus 2 Cl minus this. So, it is combined. Okay. Now, here it is all are combined. In that case, these are the equilibrium expressions we can write, and we can write beta term. In the previous case we have written K1 K2 in this way, here it is beta way because it is the formation constant, okay, or stability constant. Okay. And we will see, if we just do the homework, we will see that beta 2 is nothing but K1 K2, beta 3 is nothing but K1 K2 K3, beta 4 is nothing but K1 K2 K3 K4 like this. And instability constant, if you take the reciprocal of beta term, then it will be the instability constant. Now, it is written as K instability, K inst, and then this is just the reciprocal. So, in case of beta 4, this is the reciprocal of this one. You can see if you take the reciprocal of this one, then it will become like this. Using, why we are doing this? Using these expressions and the equilibrium constant values, it is possible to determine the concentrations of different species as mentioned above at certain conditions. Say for example, you have a system where mercury 2 plus concentration is known, conditions are known, then chloride concentration is known. Then you are able to tell me how much is there as HgCl plus, how much is there as HgCl2 plus, how much is there HgCl3 minus, like that. All species how much is present. If you know the equilibrium expressions, if you know the K values, then you can easily tell how much amount, how much is the concentration for each species. Okay. So, this is the but this is a very complex case, but previous one like silver amine complex, it is a very simple case. Okay. In that case also you can determine that. Now, the references are these are the references, and in the Swire-McCarthy particularly this mercury reference is there, mercury chloride species, that formation is there, and there is one example also shown. As I told in the previous slide, using these expressions and equilibrium constant values, you can determine the different species. There is a very nice example there. You can solve it. You can solve it by yourself, because you know the concept now. You can solve it by yourself, and finally you can see that whether you have done it correctly or not. If you can do it correctly without seeing the book, the solved problem, then I will know that okay, you have understand what is explained here. Okay. So, please try that. This is a very good example actually to learn, and I hope that you can solve it without seeing the solved problem. Okay. Thank you.